Hello everyone, we're Team 2 from Section 3, and we're proud to present our Ceres Hopper and Sample Return mission, also known as CHASER. This is our CHASER mission design team. I'm the lead engineer, Alden Huang.
I'm the mission design engineer, Carl Lopez.
I'm the low-thrust propulsion expert, Ashley Chavez.
I'm the sample recovery designer, Alan Chen.
I'm the planetary geologist, Sergio Frausto.
I'm the systems engineer, Bryce Mullally.
Here's an outline of our presentation.
Moving on to our mission overview, we had 7 major mission goals. We were going to launch from Earth and enter a parking orbit, after which we'll perform an interplanetary transfer to Ceres. During the transfer, the spacecraft will perform a Mars flyby, after which it will rendezvous with Ceres and enter a polar orbit. While in polar orbit around Ceres, the spacecraft will perform reconnaissance on the landing sites. After reconnaissance, the spacecraft will receive a lander to retrieve multiple samples from 3 landing sites. After the samples are retrieved, the lander will return to the spacecraft, and then the spacecraft will return to Earth with the sample, leaving the lander in orbit around Ceres. We used 5 major mission concepts, the first being Hoyman transfers to get rough estimates, followed by flyby dates and optimization using MATLAB. We also used MATLAB to develop pork chop plots, which then we used to minimize the C3. And finally, we visualized and verified trajectories for the spacecraft with FreeFlyer. Now for some information on our mission background. For our Impulsive launch vehicle, we used the Space Launch System Block 2. For the low thrust launch vehicle, we used the reusable Falcon Heavy. Our targeted launch dates are May 2036. Our targeted mission duration is 7.5 years, and our mission is designed to retrieve multiple surface samples from 3 landing sites. And a short outline of our analysis. We're first going to go over Earth departure, followed by the interplanetary transfer and Mars flyby. Third, we're going to go over the Ceres arrival and sample retrieval, followed by the Ceres departure and Earth returned, as visualized in our FreeFlyer animation over to the right. And we use multiple softwares in our calculations. The main ones being MATLAB and Malto, which is the mission analysis low thrust optimization software.
So now we'll be showing how to simulate our impulsive trajectory. Some key assumptions to point out on the left is that we assume we'll be using an SLS Block 2 launch vehicle. We also assumed our spacecraft will be using a bipropellant thruster with a specific impulse of 311 seconds. We also assume that the samples retrieved from Ceres has a negligible mass. Here's also a list of theories and key physical constants we used on the right. Now here's a slide showing our optimal trajectory results from MATLAB. First, on the left, we have the Earth to Ceres with the Mars flyby. As shown, we decided that to have an optimal solution, we had to minimize our C3 in order to maximize our launch mass capacity. For this, we also assumed that we'll be rendezvousing with Ceres at a 50-kilometer altitude. On the right, we have a return trajectory from Ceres-Earth. For this, we decided that an optimal solution was to minimize arrival delta V in order to ensure a feasible return to Earth. Now, when we plot our trajectory results for the Earth-Mars-Ceres leg, we get something very close to the trajectory provided by NASA Aim's trajectory browser, as shown on the right.
All right, continuing with our analysis, here's our delta V and mass budget calculations. From an earlier slide for Earth-Mars-Ceres transfer, we were able to minimize our launch C3 to 35.5 kilometers squared second squared. We then used that performance data provided by SLS Block 2 to interpolate a launch mass capacity of about 28.8 thousand kilograms. At the bottom here, we have a table outlining the various mission sequences along with their delta V and mass contributions. Something important to note is that we have a separate landing and ascent module of about 300 kilograms. By having a separate, we're able to decrease our final Earth arrival mass requirement to just 900 kilograms. And the final mass shown in bold shows that we will arrive Earth with excess mass of about 100 kilograms. And when we sum up our budget, we will basically get a total propellant mass of about 27K kilograms and a total mission delta V of about 12 kilometers per second. Here we have a nice pork chop plot for the Ceres to Earth return trajectory simulated from 2035 to 2045. From this, we were able to find our minimum Ceres departure C3 on 2042. Here is another pork chop plot for the arrival V infinity for the same return trajectory from the previous slide. And lastly, here's a quick illustration from FreeFlyer to show the return trajectory from Ceres back to Earth.
Now, moving on to our low thrust trajectory using Malto, we use similar theories and physical constants shown on the right. This time we were able to use a Falcon Heavy reusable launch vehicle since our low thrust maneuver requires much less propellant mass. Our spacecraft uses 2 solar electric propulsion systems with an ISP of around 1600 seconds. Our landing and ascent module uses a similar propulsion system as our impulsive maneuver with an ISP of 311 seconds. So just like what was shown with the impulsive maneuver, we also have our delta V and mass budget calculations with similar sequences. We can see here that we arrive back at Earth with a final mass of 921 kilograms, leaving an excess of 21 kilograms, assuming the landing and ascent module does not return. When we sum up our budget, we get a total propellant mass of around 2,500 kilograms and a total mission delta V of around 15 kilometers a second.
This plot is generated by MALTO, or Mission Analysis Low Thrust Optimization, a program for low thrust trajectory design. We start our trajectory to Earth, followed by a flyby to Mars, where the spacecraft continues on to Ceres, where it stays for over 2 years, then coming back to Earth. The masses displayed are not the actual masses of the spacecraft. Instead, they were used to calculate the mass change ratio. Malto also does not take into account the hops on Ceres, which will be explained later on. Over on the right is the trajectory mismatches, which is the difference between our simulated and ideal physical properties. As you can see, our mismatches for position, velocity, and mass are incredibly small, meaning that we are on the correct path. The red arrow shown on the plot is where the SPT 140 Hall thrusters create a thrust maneuver on the trajectory.
Our mission has selected 3 landing sites to visit. First, the Orvara crater is a crater more than 100 million years old and provides very smooth terrain for the initial landing sequence. The Okata crater is suspected to have a water source and have salt deposits at the surrounding. For the Hunamans is a peak more than 4 kilometers high. The spacecraft will land at the edge of the hill, and this location is expected to have cryovolcanic activities and also have very rich salt deposits. Using FreeFlyer, we were able to get the dates where the spacecraft will intercept the Orvara crater, as seen on the right. The graph on the left shows the logical indices where it shows true that the spacecraft is right above the landing location. For the Ceres descent and ascent delta V calculation are basically the summation of the different velocity components, which are the orbital velocity of this orbiting spacecraft, the landing site velocity due to Ceres rotation, and the gravity loss velocity component. These sequence will be performed using the landing and descent module. Note that for descent, we will have 1 burn canceling out the orbital velocity and another burn to ensure we have a soft touchdown. But for the ascent, we will use just 1 single burn, and we will land at the Orvara crater on April of 2040. To visit the other 2 landing sites, we will perform suborbital hops as visualized on the right. We will have 1 burn for the liftoff and 1 burn for the landing. We will visit the Okata crater on February of 2041, the Hunamans on August 2041, and we will lift up from the Hunamans to rendezvous with the orbiting spacecraft, and the module for landing and descent will be left at Ceres orbit.
This is our final design overview. To the left, we have our impulsive maneuver, and to the right, we have our low thrust maneuver. The 2 differ on the first 2 bullet points, the first being total propellant mass. This is due to the fact that the impulsive maneuver has 10 times more total propellant mass compared to the low thrust maneuver. The second thing both maneuvers differ is the total mission delta V. The total delta V on the low thrust maneuver is 3 kilometers per second more greater than the impulsive maneuver. And the remaining 3 bullet points, both maneuvers are similar in final mass at Earth, V infinity at Earth, and total mission duration, which is about 10.75 years. Here we have our mission timeline. On top we have our impulsive maneuver, and on the bottom we have low thrust maneuver. Both have very similar dates throughout the mission, such as Earth departure, Mars flyby, Ceres capture, and Earth arrival dates. Where the two differ is that the Impulsive maneuver has a longer Ceres stay time of about 6 months. Now to summarize the entire Chaser mission project, we will briefly go over how we met our mission requirements. Just to highlight a couple, we were able to meet our second requirement, which states that the entire mission duration should be less than 12 years. This was the timelines in the previous slide. Another is our Earth arrival V-infinity requirement, which we verified through technical calculations using MATLAB and Malto. As shown in our final design slide, we were able to verify that both Impulsive and low thrust maneuvers met all requirements. In addition, Chaser was able to perform a Mars flyby and visit multiple Ceres landing sites. And in conclusion, we determined that the low thrust maneuver was more efficient because it required 10 times less total propellant mass due to the difference in ISP.